I want to talk about 4 key areas in which Google Cloud can help mobile developers, desktop developers, or any developer code, build, run, and observe their applications better using Google Cloud Platform. And we're going to focus on 4 key areas. And there are other areas. These are just the 4 that we've chosen in the short 40 minutes that we have today. The first is code. We're going to talk about how we can leverage Google Cloud services to build backend systems to support our front-end mobile and desktop applications. Next, we'll talk about how we can leverage Google Cloud artificial intelligence and machine learning technologies to build intelligence and business logic into our applications. Then, we'll talk about how you can build and publish your applications leveraging the power of the cloud. And finally, after we published our applications, we'll talk about how we can gain insights into how they're performing and how they're communicating with one another by talking about observability. In order to do this, my colleague Dale and I have come up with this idea for a fictitious application. It's a food delivery application. Now, we know there's many food delivery apps out there, but ours is going to revolutionize the market. Ours is specifically going to leverage Google Cloud Platform technologies, and we're going to use it to show you how you can leverage those technologies in your mobile and desktop applications. So let's go ahead and jump over to the laptop, and I'll show you a quick demo of what we've built here for you today. I'm going to do something super taboo. I'm going to show an iPhone at an I/O demo. Cool. So I know this looks like a movie recording, but this is a real. I'm using my iPhone, so you all can see that this is real. We have 2 apps here. We have an app called G-Eats and an app called G-Eats Admin. I'm going to show you the G-Eats app first. So I'm going to go ahead and open up the G-Eats app. And this is the application we built here for you today. It's actually built using Flutter. Can we get a shout out for Flutter? Sweet. So even though I'm using an iPhone, this actually cross-compiled to Android just fine using the same exact code. So what I'm going to do here is I'm going to order from Googleplex. Googleplex is our fictitious restaurant that we're working with here today. I'm going to add a Caesar salad because I'm on a diet. I'm going to add some grilled cheese because I'm on a diet, and cheesecake because I'm on a diet. I don't know what kind of diet y'all are on, but I'm on a fun one. So here I have my Caesar salad, my cheesecake, and my grilled cheese. They're in my shopping cart, and I'm going to go ahead and click checkout. Now, in order to fulfill our narrative, our application has had some fraud in the past. Specifically, people have stolen friends' iPhones and Android devices and ordered, it's the old order 10 pizzas to your house trick. So what we've decided to do as a product team is implement a text message verification. So whenever I click send confirmation, my application will generate a text message with the total order cost. It will send me that text message. And then I have to, oh, my mom said she loves me. And then I have to reply yes or no to this text message. So we can see that the order is 1950. We have a fun bug there. It doesn't add the 0 after 50, so you know this is production ready. And I'm just going to go ahead and reply yes. And within a few seconds, we'll get a response back that says, thank you for your order. It will arrive soon. And this is the kind of the consumer or the front-end application we've built, and it's a mobile application. So let's go ahead and jump back to the slides, and we'll talk about the technologies we used here specific to Google Cloud. So if you've ever built a mobile application, oh, that was our video in case it failed. We've done this before. So if you've ever built a mobile application, especially using Flutter, you know that we use the standard Material UI components. These are some stock images. Nothing super complex there. But if you've ever built a mobile or desktop application, you know that sending and particularly receiving a text message is very difficult. While you might be able to leverage the local phone to send a message, you don't have access outside of the sandbox to receive that message and do any kind of processing with it. So this is where we need to leverage a cloud service in order to send and receive those text messages. And this provides a perfect opportunity for us to showcase the first of many ways in which Google Cloud Platform has invested in making the coding experience for backend services and supporting services quick and easy. It all starts with code. Whether you're a mobile developer or a desktop developer or a firmware engineer, it all starts with code. And for the past year, we've invested heavily in the developer tooling ecosystem to bring you really great developer experiences, regardless of the technologies you're working with. Specifically, we don't want you as a mobile developer or an application developer to have to provision servers, create users, install packages, install security updates. We want to do all of that for you as a cloud provider. Some people call this serverless. It's the idea that you give us your code and we run it for you. We scale it for you, and we keep it running for you while giving you observability into it. Let's go ahead and jump back over to the laptop, and I'll show you exactly what we mean. So here, I have a very small Node.js application. It's about 100 lines of code, 105 to be exact. It uses the Express library, and the important part is that it has two endpoints. The first endpoint is send, which you'll see right here. This accepts input from our application, our mobile application. It hits this send endpoint, which then communicates with our third-party API, Twilio in this example, to send a text message to the user. Then, we have another endpoint, which is verify. Verify receives a webhook from our third-party API service whenever a user responds to a text message. It includes the body of the text message, and we can build branching logic and process that response. So you'll notice here we have about 3 or 4 lines of branching logic here where we see, did the user say yes? Did the user say no? And otherwise, we send them in kind of a hot loop saying, you got to say yes or no to this order. Now, this is obviously like a fictitious application. We don't actually dispatch an order to the Googleplex Cafe because it doesn't exist. But you can this gives you an idea and hopefully some inspiration as to how you could leverage a service like this to build something very powerful. But now what? I have this Node.js code. It's on my local laptop. Now what do? I obviously run Node locally and install ngrok and keep my laptop up in production all the time. That's probably not a great idea. So how can I get this code, which is on my local laptop, to be running somewhere that my users can access it and this third-party API can access it? And this is where Google Cloud Functions comes in. So I'm going to go ahead and change directory into our code file here. And inside here, you'll see, just do this. Inside here, you'll see our Node application. And the important file that I just showed you is that index.js file. That was the code that we were just looking at. Now I want to deploy this code to a publicly accessible endpoint. And I can do that using Google Cloud Functions. So I'm going to show you what this code looks like. And I'm really bad at typing live on stage, so I've just typed this out as a script in advance. If you're not familiar with scripting, the first 2 lines just say interpret this as bash. The importance part is the gcloud functions deploy. This uses gcloud, which is the Google Cloud SDK. You can install it on your Mac, on your Windows device, on your PC. And we're deploying a function called SMS. This is our kind of our SMS gateway, if you will. I'm specifying the project in which to deploy it, the runtime. In this example, we're using Node.js. We'll talk about some other runtimes in a minute. I'm giving it the entry point where it should listen. And finally, I'm telling it to be an HTTP trigger. There are other kinds of triggers, like pub/sub. But for this example, we're using HTTP. When I run this, the gcloud deploy command will bundle my code for me locally. It actually bundles it into a tarball. It sends that tarball up to the Google Cloud Platform servers, where the Google Cloud Platform will build a binary distribution of our application and run it for us. And this is Google Cloud Functions. It's actually just that easy to take code that you have locally on your laptop and have it running at an available HTTP endpoint somewhere on the internet. And by default, it doesn't have any authentication, but you can add your own authentication, either using your own frameworks or using Google Cloud IAM, Identity and Access Management. So this is deploying. It takes about 2 minutes. Let's go ahead and jump back to the slides, and we'll talk about Google Cloud Functions in more detail. For this particular example, we leveraged Google Cloud Functions to deploy our supporting backend SMS service. Our particular function was written in Node.js, but it could have been written in Python or Go as well. Node, Python, and Go are the 3 languages that we support today in Google Cloud Functions. And for many of you in the audience, you'll be excited to know that we're currently in a private alpha for Java support. So if you're leveraging Java technologies, You'll soon be able to leverage those in Google Cloud Functions. But what if you don't use those languages? What if you're using some other language, Rust or Ruby? Or what if you have additional requirements beyond just 100 lines of code? Maybe you do have some system-level dependencies. Maybe you're interacting with robotics, so you need the robot operating system available to you. Maybe you need access to different things. And this is why we introduced Cloud Run just a few weeks ago at Google Cloud Next. Cloud Run is the latest edition of our serverless offerings. Remember, we talk about serverless, we mean don't manage any servers, don't install any packages. With Cloud Run, you package your application and all of its dependencies into this thing called a container or a Docker container. And then Cloud Run scales that container for you automatically. You run the gcloud command to deploy your function to Cloud Run. Cloud Run will automatically scale your function, and it'll even scale it down to 0. And this is very important if you're an early-stage startup or a mid-sized company that's tight on a budget, because with Cloud Functions and Cloud Run, you only pay while your code is being run. You don't pay if no one is accessing that endpoint. And if all of a sudden you have 1 million users who are all accessing that endpoint, we'll scale for you automatically. And we'll automatically scale back down when that traffic alleviates. That's code for you. Now, to tell you more about how you can leverage AI and ML, I'd like to invite my colleague Dale onto the stage. Please give it up for Dale.
Thanks, Seth. Hi, I'm Dale. I'm a developer for AI and Google Cloud. So let's talk about how we can add a little intelligence into our app to make it easier to use. And why might we want to do that? Well, you saw Seth's nice Flutter app for ordering food. But let's say that you're a restaurant and you want to get listed on our app. Oops. Then you probably have a menu that you need to upload. And your menu is probably analog, so you need to have somebody manually type in all of the foods and prices and all of this metadata to become listed in the GEADS tool. And that's really annoying, especially if you're trying to do this on mobile. So can AI help make that part of our app easier? Let me show you how. Let's hop to the phone. I'm clearly a Pixel user. All right, cool. So you saw this nice app that Seth built, but let's look at the admin side that a restaurant owner would use. As you can see in this interface, there's no text field for writing foods or prices. Instead, we just upload a photo of our menu. That photo gets uploaded to the cloud and analyzed, and that analysis can take a few seconds. So let me show you the picture that I just uploaded. This menu I was holding on stage. And as you can see, there's lots of useful information here, like the name of our cafe, its address and phone number, plus all of this food information, like the headings, salads, mains, the food items, and their prices. So let's hop back to the phone. And look at that. We got lots of information from our menu without even having to type it in. Let's take a look at it. So we identified Googleplex Cafe, its phone number and address. We also got these nice little rating stars and a map showing where a restaurant's located, and this cool user-generated picture of the Google headquarters. We also did a pretty good job of parsing the foods on the menu, the descriptions, a veggie burger on a pretzel bun. I also want to point out that this part wasn't 100% perfect, like we didn't identify the price of the chili, or we thought that cherry lime was a food and not a type of gelato. But we still saved a lot of time, and we can always go in and edit those specific details. So how did we make that possible? Let's head back to the slides. So let's just recap what just happened. First, I uploaded a photo. Then we took the photo and extracted it into text. Then we determined the location, the rating, and we pulled some photos. And then we also parsed the menu itself, the foods and their prices. So how did we do it? To get the text, we used the Google Vision API. And once we had our menu in text format, we could pass it to the Google Natural Language API. This tool has lots of useful functionality for analyzing text, But we just focused on the entity extraction feature, which finds substrings in our menu text that correspond to prices, phone numbers, addresses, and more. And once we extracted that phone number, that was very useful because we could use it to query the Google Places API. So Google will take a phone number, and if it recognizes that that phone number corresponds to a place, it can return you useful metadata like the star rating of the restaurant, user-generated photos, location, and more. But actually, the most difficult part about building this app was identifying those menu-specific entities, like that grilled cheese was a food, and that on a pretzel bun was a description of a food. Because that's so specific to our context of menu parsing that there's nothing like in the box in a Google API that recognizes these terms. For that, we had to build a custom model, and we did that using a tool called Google Cloud AutoML. The way that works is you upload a labeled training data set, AutoML builds a model for you, and then it hosts your model in a REST API that you can call to get predictions. But rather than explain this, let me just show you a demo. Let's hop to the laptop. So here I am in the Google Cloud Platform console, and I'm in the natural language AI tool space. And there are lots of different types of text models that we could build, but we're going to build an entity extraction model. That's for identifying inline text items. So our first step is to find a data set and upload it. And I tried a few, and this one worked the best. And so what happened was I found this data set provided by the New York Public Library of pictures of historical menus that had been uploaded. And I used the Vision API to extract the text from them. So let me show you what that looked like. Easy Beef, a restaurant in Virginia. And then I went in and I hand-labeled all of the entities that I cared about. Just did that by clicking and dragging, and then saying, a cheeseburger is a food. And after I did this for about 2 hours, I got really bored of labeling data. This is the very boring part of building machine learning models. But luckily, Google now offers a data labeling service, where if you want a data set like this, you can send it to the labeling service. Google will label your data, and then you'll be good to go. One thing I'll also point out is that I didn't have a ton of menus to work with in that data set, only under 200. And ideally, when you're building a model like this, you really want more like 1,000. But as people use our app, we'll collect more data, so that's fine for now. Now we want to train a model to be able to do that annotation for us automatically, and that's actually the easiest part. We just click Start Training, and then we'll get a pop-up that says something to the tune of, all right, come back in 4 hours, and you can see your model. And then behind the scenes, Google will train a model for us. If we hop into this Evaluation tab, we can see all sorts of useful metrics about how accurate our model was. And like I said, more data means more accurate, so hopefully over time our model will improve. And then in the Test and Use tab, we can actually make predictions. So I think I opened this because I couldn't write a menu on the fly. But I came up with this little fake menu. I'll press Predict, and we'll see if our model can correctly identify the entities. And as you can see, it identified all of the entities imperfectly, because that's machine learning, and machine learning has an element of probability to it. But if we were to use this in our app, it actually does save us a lot of time inputting data, right? Because it identified most of the foods. It missed potato chips, but it was pretty good. And then as users correct us in the app, we'll have more data to retrain our model. By the way, this is how to use the app in the console, but you can also hit it with a REST API or through a number of client libraries. All right, let's hop back to the slides. I just showed you how to build an entity extraction model, but actually there are AutoMLs for all sorts of different data types like photos, video, and more. And if you want to learn more about this, make sure to check out my session tomorrow at 12:30. But with that, I'll hand it back to Seth.
Awesome. Thank you, Dale. So far, we've showed you how Google Cloud enables you to focus on your code by deploying scalable backend services using Cloud Functions or Cloud Run. And Dale just showed us how to add intelligence to our applications by leveraging Google Cloud ML products like AutoML. And I have to say that I'm an engineer that focuses on infrastructure and operations. And prior to this talk, I had no idea about anything other than machine learning besides magic. And Dale has taught me a lot about how we can leverage different Google Cloud technologies without a PhD in machine learning. And I feel like an expert now. I'm not, but I feel like an expert. So next, let's look at how Google Cloud can help us with our builds, specifically our mobile application builds. So we have this Android application code. Again, this is Flutter, but it could be anything. And we have these AI models. Now what? How do I get that in the hands of my users? Now, I could leverage something like the Android Build Studio locally on my MacBook. That would build my application. I could publish it to the Google Play Store. But my local laptop is not a hermetic environment. I might have packages or users or configurations that will cause my build to fail, or worse, pass incorrectly by linking to a system library or using the wrong version of Java or the wrong version of the Android SDK or NDK. We don't want this, especially if you have many different developers, especially across many different organizational units. You want a consistent central build environment where you can control things like versions, variables, substitutions, packages, etc. And this is where Cloud Build can come in. Cloud Build enables us to use the scale and elasticity of the cloud to build and publish our Android applications. With Cloud Build, we can build and test our applications in isolated hermetic environments, leveraging the scale and elasticity of the cloud. Most importantly, we only pay for the build time that we're using, and there's a very generous free tier to get started. So with that, let's go ahead and jump over to the laptop, and I'll show you exactly what we mean. So I'm going to go up here to my build directory. So in here, I have an Android application that's built using Gradle. Now, I totally could open this up in Android Studio. I could click Build. I could deploy it to a phone. And I bet that many of you in the audience have already done that before. But how do I get this in the hands of my users? Well, I could build it locally using the Android Studio with a production build. But I want to leverage the power of the cloud. For me to build this locally takes about 10 to 15 minutes with my dual-core i7s. But what if I could use, say, 32 cores to build this app? That would hopefully be very fast, but at the same time, it guarantees that nothing on my local laptop is interfering with the build, having it fail or pass improperly. So let me show you how we submit our Android build to Cloud Build. Just like before, I have a script because I'm not good at typing on stage. Let's jump down to the very bottom where we have gcloud build submit. We're running a build by submitting all of this code in this directory, all of these Android manifests and Gradle files. We're sending all of that up to Cloud Build. We're running our build on a high CPU 32-core VM, and then we're passing in some substitutions. What are these substitutions? Well, in order to build an Android application, we need the Android NDK, or we need the Android SDK, and potentially the NDK. But every time I build my application, I don't want to recompile the entire Android SDK. I don't want to have to download it and install it and all of the dependencies. With Cloud Build, what I can do is I can cache those different layers of my build steps. So I can download, say, the Android SDK 27. I can cache that as a build layer. And then when I'm ready to deploy my application, I pull that build layer down, and I just build against it. And then anyone else in my organization that's building Android applications builds against the same base layer, the same base image, and that guarantees some consistency across our applications. I'm going to go ahead and run this now. Now, there are 3 machine types for Cloud Build. We have a single core, an 8-core, and in this example, the 32-core. I ran this particular build across all 3 instance types. Takes about 15 minutes on the single core, about 3 minutes on the 8-core, and about 2 minutes on the 32-core, which is what we're using here today. But I don't think you all want to stand here and watch log stream for 2 minutes. So let's go ahead and jump back to the slides. We might come back to this output if we have time in a bit. So let's recap what just happened. I have an Android application, code. I submit that code to Cloud Build. And Cloud Build can build anything. Ruby applications, Python applications. Today, we're building an Android application. Cloud Build not only compiles my application, but it also runs any tests that I have for me. Then it uploads the compiled APK file to Google Cloud Storage, which is our object store. From there, you can download it, load it onto your test devices, give it out to trusted users for feedback. What we didn't do in our example today is publish directly to the Google Play Store. However, you could use the Google Play Store APIs to publish directly to a beta or test channel on the Google Play Store. And on the other side, Cloud Build actually integrates with source control, like GitHub and Git, and supports these concepts of build triggers. So you can imagine a world where you build a CI/CD pipeline for your Android applications, such that when you merge a pull request or merge a change request, within 10 to 15 minutes, that change is available as a beta build to your users, all in an automated fashion, only paying while your build is running. This is truly leveraging the power of cloud. But now what? We have our application. It's in production. Hopefully, we have some users. Right now, the G-Eats app is really popular. There's 2 users. It's Dale and I. But now what? We're done, right? No, we have to talk about observability. How do we gain insights and metrics into our application? So let's come up with another hypothetical scenario. Or sorry, let's talk about observability first. What is this thing that I'm saying? I'm saying this word, observability. Observability is an umbrella term that describes things like monitoring, logging, alerting, tracing, dashboards, and much more. It allows us to gain insights into a single application, but also how our applications are communicating with one another. So now let's look at a hypothetical situation. Let's say on social media, we get a message like this. Hey, I really love your new food delivery app, but sometimes it's really, really slow to get my text message. Sometimes it takes nearly 5 minutes to arrive, and I'm really hungry. Now, as an application developer who's generally internet savvy, I could quickly write this off. Clearly, they're not in a good they don't have good cell phone reception. That could explain the latency, right? Or maybe it's an issue with their cellular provider in general. Maybe it just takes their cellular network provider time to deliver. Or maybe they have an old phone, can't process the messages fast enough. But what if I could actually prove it? What if I could get a message like this from my support team or my social team, and I could definitively go back to them and say, nope, this is definitely not our problem. This relies somewhere else outside of the chain that we don't control. And in order to do that, we can leverage a tool called Google Cloud Stackdriver. Stackdriver is a tool for observability. It provides integrated logging, monitoring, alerting, and tracing across Google Cloud that allows us to gain better insights into our application's performance. Let's go ahead and jump in to the auto-generated Stackdriver Chase dashboard to confirm that our text messages are being processed quickly. So let's go ahead and jump over to the demo laptop. Here, I have the Google Cloud Trace dashboard in our web console. And I'm particularly filtering on an endpoint, which I've coincidentally named slow for the purposes of this demo. Now, I realize that some of you may not understand what you're looking at, so give me a moment to explain it. First, we're looking at the past hour of traces, which is a measure of the different steps that our code is taking across our different services. On the left-hand side, we're looking at a data point, a sample of a data point, and on the y-axis, it's the latency or the total time it took that request to fulfill. So a dot here, for example, took 20,000 milliseconds. That's 20 human seconds. Whereas a dot down here took 340 milliseconds. That's less than half 1 human second. Now, we can look at this and we can say that most of our requests are down here at the very bottom, which is good. It means they're being processed very quickly. Ideally, we want low, low, low latency. So we can see that most of our requests are being processed in about 300 to 400 milliseconds, which is really good considering that's a mobile application going over the public internet, invoking our endpoint, which is communicating with a third-party API, and then returning a response. So 500 milliseconds for that round trip is really, really good. You'll notice that we have a few here that are about 3 or 4 seconds, but those don't concern me. That could just be network latency. But these ones up here, that's concerning to me. Those are definite outliers. They're 20 times and 40 times longer than any of our other traces. So let's take a look at the difference here. Maybe we can gain some insights into our code. If I look at one of these traces that took about 300 milliseconds, scroll down a little bit, you can see that our endpoint was dispatched. Then, about 5 milliseconds later, 10 milliseconds later, it actually hit our code. And then about 3 milliseconds later, we dispatched our third-party API. Very quick, very fast, very expedient. Now let's take a look at one of these outliers up here. Now we notice something very interesting. Our request, again, dispatched very quickly. There's only a few milliseconds between when we hit our endpoint and when our function was actually invoked. But then there's a huge block of time, almost 20 seconds, until we call our third-party API. This is actually an indication to me that our initial hypothesis is wrong. This is a bug in our code. We're not waiting for the third-party API. We're not waiting on network latency. This is all within my application, and I know that it's happening inside the SMS slow endpoint. This gives me immediate insights into where to go to look in my code for a bug or a performance issue. So let's take a look at that. And it turns out if we jump down here to our slow endpoint, there's actually a random 10% of the time we sleep for 20 seconds. And there's a really embarrassing to-do here that I was supposed to remove this before going to production, and this was just for local testing. And then we send a test message. And now I know no one in the room has ever accidentally pushed local test code to production. But if you had, hopefully it's clear how a tool like Stackdriver Trace made it easy and apparent that this was our fault. And we can go to our support team and we can say, hey, your users are right. 10% of the time we were making them wait 20 extra seconds. We fixed that. It's not going to happen again. And we built monitoring and alerting around it so that we can proactively detect it in the future. Let's go ahead and jump back to the slides. So to recap, today we discussed 4 areas in which Google Cloud Platform can improve your developer experience. First, we talked about code. We talked about how you can leverage tools like Cloud Functions and Cloud Run to build scalable, serverless applications to support your mobile or desktop apps. Next, we talked about leveraging Google Cloud artificial intelligence and machine learning products to build intelligence into your applications without needing a PhD in natural language processing or machine learning. Then, we showed how we can leverage the power of the cloud to build our applications on multi-core VMs, leveraging elasticity in a hermetic and isolated environment. And then lastly, once our application was ready to go, we saw how we can diagnose and analyze that application when it's in the hands of our users by tracing our backend services, leveraging Stackdriver Trace. This has all been in service of one high-level goal. And if you're going to take anything away from this session today, this is what Dale and I want you to leave with, is that you should focus on your code and let cloud do the heavy lifting. We are investing resources in making sure that we are not getting in the way of your core business. We want to support the business with these different tools and technologies. Let cloud do the heavy lifting. If any of this was interesting to you, I'd like to invite you to attend our other cloud sessions. You can click on Cloud in the app or on the mobile web interface. Specifically, I want to highlight these 4 sessions. For a general overview of many different Google Cloud services, check us out on stage 7 at 2:30 tomorrow. As Jill already said, she has a talk later tomorrow about training a custom machine learning model without any data science experience required. If you're concerned about the security aspects of this, there's a really great session tomorrow at 4:30 talking about how you can secure your applications while leveraging Google Cloud. And if you were at all interested in that serverless stuff, Google Cloud Functions, Google Cloud Run, App Engine Flex, there's a great session tomorrow at 6:30 on making the right decisions for your serverless architecture. So with that, I'd like to thank you all very much for coming. Dale and I will be happy to take questions in the sandboxes down here on the stage, or feel free to tweet at us as well. Thank you all so much.